Lesson 7.3, liquid vapor equilibrium. So liquid vapor equilibrium exists in a closed system, and when you have a liquid, gas particles will escape from the liquid until the rate of evaporation equals the rate of condensation, until it reaches equilibrium. So here's an example. Here's a liquid, okay, and the liquid particles are going to escape into the gas, break free of those intermolecular forces, and those gas particles are also going to come back down, condense back into the liquid. And when this happens at equal rates, then we have reached equilibrium. The vapor pressure is the pressure exerted by a vapor on its liquid, and during equilibrium it remains constant. The vapor pressure does not change. So when you have a high vapor pressure, the equilibrium lies to the right because you have more gas. If you have a low vapor pressure, the equilibrium lies to the left because you have more liquid. So how can you change the vapor pressure? Well, there's a few things that vapor pressure does not depend on. Vapor pressure does not depend on the surface area of the liquid, nor does it depend on the volume of the liquid or the vapor. So the boiling point. The boiling point is when the vapor pressure equals the external pressure. So when the vapor pressure outside of the liquid equals the external pressure, then the molecules are able to escape the liquid and become a gas. So what happens to the boiling point at high altitudes and why? Well, at high altitudes, the external pressure is lower because you have less atmosphere above you pressing down. So the boiling point is reached much sooner. The liquid is able to escape to a gas much sooner at a lower temperature at higher altitudes. So because it escapes at a lower temperature, your food is really not cooking as long, for example, up there, which is why on boxes, oftentimes there's high altitude directions, which is why at high altitudes there's oftentimes directions to show you that you have to cook your pasta longer because it's actually boiling at a lower temperature. Okay, this is where pressure cookers come in handy, because in a pressure cooker you increase that internal pressure, that pressure that's needed in order to boil, so you actually boil at much higher temperatures, which cooks your food faster. So the higher the pressure, the higher the boiling point, and in a pressure cooker the water reaches 120 degrees Celsius without boiling, because again that external pressure is so high that the molecules have to reach 120 degrees before they can escape into the gas. This decreases your cooking time. The same concept is applied in what we use in what we call an autoclave. An autoclave sterilizes lab equipment, similar to surgical equipment. The second thing that affects the vapor pressure is the nature of the substance. So the stronger the intermolecular forces, the more energy required to break them, which means that less particles evaporate and the vapor pressure is lower. So here's an example. Here we have water, which has hydrogen bonding. So here's an example. Here we have water, which has hydrogen bonding, ethanol, which has one hydrogen bond, it's a little bit longer molecule, and diethyl ether, which does not have hydrogen bonding. And you can see that the ether boils a lot easier because it doesn't have such strong intermolecular forces that it needs to escape in order to boil. Volatile substances have high vapor pressures, meaning that they boil at low temperatures and they have weak intermolecular forces. So things like nail polish remover are very volatile. They have low boiling point. That's why you smell them more. An example also would be bromine. Bromine boils at 58.8 degrees Celsius, which is really not that warm. Now if you think back to topic 5 from last year, remember that we have an enthalpy of vaporization. So remember that vaporization is endothermic, meaning you have to put energy in to get something to evaporate. It has a positive delta H, therefore, and the enthalpy of vaporization is the energy required to convert 1 mole of a liquid into a mole of a gas. So here's an equation showing a liquid X going to a gas X. So the stronger the intermolecular forces, the higher the enthalpy of vaporization. You need more energy, the higher the boiling point.